Afternoon to one and all gathered here. Today I am welcoming Jignesh Wala sir, Professor Jignesh Wala. He is from SVIT, Sardar Vallabhbhai Patel Institute of Technology. He is assistant professor and currently he is pursuing his PhD degree from mechanical engineering, and he did his ME from jet propulsion in the field of jet propulsion in jet propulsion and gas turbine plant from the Faculty of Technology, MSU, uh, University of Baroda, and he is holding a bachelor degree in aeronautical engineering from the Sardar Vallabhbhai Patel Institute of Technology, Rotor. He have 8 years of teaching experience and 1 year of industrial experience, and he had completed his he has published more than 20 research papers in various national and international journal and conferences proceeding, and he has guided so many students of UG research project, and he have the area of research in the field of aerodynamics, computational fluid dynamics, propulsion, and turbo machinery. So we are welcoming you, sir. Please, sir, go ahead. Thank you, sir, for accepting, and welcome you, sir.
Thank you very much for the such a very nice introductory question, ma'am. Thank you very much, Nikita ma'am. Uh, good afternoon to all, one and all present here. I'm going to presenting the introduction to turbomachinery using the CFD methodology. First of all, we'll discuss about before we will proceed the more in turbomachinery part, and especially for the using the computational fluid dynamics, we must to understood the meaning of fluid flow. Why we will deal with the fluid flow? Fluid flow, there this fluid flow is very important in the field of turbomachinery, as we know that, and we know it the fluid flow that we can clearly see in the PowerPoint presentations, right? So let us look at the slides now. Uh, what you can see here, let us see what we actually mean by a fluid flow, and what are the applications, and why do we need to study the fluid flow. So this is the basically what you see here. This arrow pointing towards the right directions, and these are indicating of a fluid flow. Since these are likely a velocity vector, and velocity is a vector quantity that we know, and we know that the definition of the vector quantity. So we indicate both the magnitude and the directions, right? And this is the fluid flow. And now let us say we have a plate, and plate like standing over there, and a flat plate in front of this of the flow, and so that what happens, this is easy to imagine the what will happen, and we all know that the flow starts acting on the plate, and the plate start moving in the direction of the flow, right? So for the case of in the direction of the plate, the second image says that the a little different situations. So we have the flow and we have a plate, instead of being kept perpendicular to the direction of the flow, and we have now inclined the plate at a little bit, right? So we now what happened is this: the same situation is similar, but not actual same, that we can see that standing at vertical and this is standing at some inclination angle, right? But what happens now? The plate now moves in the different trajectories. So it moves approximately in this way. So in the first case, we have a drag force, right? And the force acting in the direction of the flow, and in the second case, we have a drag force and the lift force also. Okay, so that a force which act in the direction of the flow and a force which acts perpendicular to the direction of the flow, that we can say this is known as the lift. So this situation which is easy for us to imagine, right? And what interest to us this kind of situations or this kind of flow is that we can study fluid mechanics or fluid dynamics, right? So we can easily give the answer about it. Okay. So for the case of for the case of So as I told you, this is the lift force form, and opposite the lift force, we know very well the weight is there, and here the drag force form over the plate. So in the opposite of the drag force, the thrust is there, right? So the situations says that the kind of turbine, and you can see the flow, and you can see that we can get this kind of answer by our study of the fluid flow, right? So in the second situations, we can ask the questions like how is the lift generated? Like we have flow in the direction from left to right, and we have a force which is perpendicular to the direction of the flow. Okay, so the lift force is perpendicular to the direction of the flow. So starting from first principle, we find out how is the lift generated, right? So our study of the fluid mechanics that will help us to answer these questions. Okay. And again, from the point of view of the applications, this is very important because of these lift force is certainly needed for applications, right? So where you know flight dynamics, the flight applications like in the case of aeroplane. Okay. So there we want to do is not only we want to estimate the lift and drag, we want to reduce the drag and increases the lift. So this is our main agenda. We have to raise the value of lift. We have to raise the lift coefficient and minimize the drag coefficient. So this is our main agenda behind to improve the aerodynamic efficiency. Uh, so the the situations the situations we have different questions like that. What is the magnitude of the drag force? How is the lift generated? How to reduce the drag and how to increase the lift? Right. So we have a different situations that we discussed earlier. So which has been the demonstrated here that we can clearly see in the PPT. The plate is moving and there is the flow, but the similar situations can be thought of when you have the plate moving but the flow, the surrounding is stationary, right? So it is very similar, so that the fluid dynamically it is very similar to that. Now that is the case of an airplane that flying in the sky, right? So in that case, the drag force is actually acting against the direction of the plane, and the lift force in helping to fly, right? So helping it to support the load of the plane and also the payload. So basically lift is useful and drag is undesirable, right? So can we reduce the drag and lift? So if we can see here, I can give the example, which may all of us may be familiar with that. So take the case of a paper aeroplane, right? So that we can get that we can clearly see in the PowerPoint presentations in this figure. So we have a one paper aeroplane, and it is very simple thing. The actually aeroplane is very complicated, right? So if you see, probably all of us have made this kind of planes and small things during our school days, and flow it in during the class in the classrooms, right? Uh, so even in the making of these, so there is understanding of the fluid dynamics, right? So what motivates? Let us ask the questions that in this shape. Okay, uh, what motivates the triangular shape of this aeroplane of the paper aeroplane? The answer which I can think about, and they are the motivation to reduce the drag. right? Because when the aeroplane is flying, you can think of, if you look at it from this side, it is very similar to this plate. Okay, so lift is generated here, which held the aeroplane to get the lift after we throw in the sky, and the drag can be reduced in this case by reducing the frontal area in the plane. So the frontal area is the area which is seen by the seeing from the direction of the flow. And if we look at the plane from the direction of the flow, the area which we can see in the frontal area, so the drag is very much proportional to the frontal area, and that can reduces, right? That can we can reduce it. So we use a triangular shape instead of the rectangular shape here. Okay, so this is the simple introductory portion about the fluid flow, as well as the frontal area that reduces in the paper aeroplane for reducing the aerodynamic drag. Now come to the point of the turbo machinery. So first of all, we will break out the word of turbo machinery, turbo plus machines. Okay. So in turbo machinery, we can say that first we will understood the meaning of turbo machines. So the any device that extract the energy from, or we can say impart the energy to a continuous moving stream of the fluid, that can be called, we can say, turbo machines. And let us come to the main definitions using using in technically way. So turbo machines is a device where energy is transferred, right? And either from or to a continuously flowing fluid by the dynamic action of one or more rotating blade rods, right? So there are a number of rows. There are a number of rows in turbo machinery field. So first, the term which has been highlighted is energy is transfer, right? So which energy is transfer into the which energy is very important case. Okay. So in the fluid mechanics, in the fluid mechanics, in the computational fluid dynamics, energy transformation, it is very important, right? So the transfer of energy, and that transfer of energy take place either from the continuously flowing fluid or to the continuously flowing fluid. So that means there are two different types of turbo machines that we can say. Why the continuously flowing fluid is highlighted? This is also very important. So in contrast, from the discontinuous flow or the ripple flows, we have seen in the case of positive displacement machines. So in turbo machinery part, we can divide it into the main two different cases: positive displacement machines as well as the turbo machines. So this brings us the next item, which is the classifications of the turbo machines. So as I told you, so based on the mode of the transfer of energy and based on the working medium. So these are the classifications of the turbo machines. So the common examples are the we can say the power pump, the fan, blower or compressors, right? If on the other hand the flowing fluids has energy, and that energy is extracted by the moving blades, and that makes the shaft to rotate, and as a result the power is right. So the fluid power is converted into the mechanical energy. So this is very important. So we can say these are the power producing devices, and the examples are different types of turbine, steams, gas or hydraulic turbine, right? So the next kind of classification that we can say, uh, that based on the working medium, right? So based on the mode of the transfer of energy, as I told you, the shaft work to the fluid. The example, as I told you, the pump, fan, blower, and compressors. So this is the power absorbing devices, right? So what happened inside the pump, fan, blower, and compressor to absorb the power, and the transfer of fluid to shaft power means to produce the power. Okay, so the example is, as I told you, the steam, gas, or hydraulic turbine. The next part is the based on the working medium. So deals with the liquid in general and water in particularly like a pump, hydraulic turbine, and deals with, we can say, liquids and gases in general and air in particulars like a gas turbine, the steam turbine, compressors, blower, fan, right? So these all are the examples on the based on the working medium. So there are other types of turbo machines which handles the vapors and gas, and more particularly air. The example like gas turbine, the example like gas turbine, steam turbine, compressor, blower, fan. So we can continue with the classification of the turbo machines further. So we can say that based on the type of the flow, it is we have already studied in fluid dynamics, and that the flow can be incompressible and compressible flow, right? So we must to understood the meaning of compressible flow and the incompressible flow. As we know that the rate of change of density with respect to time and space, that is constant, so we can say this is known as the incompressible flow. And the rate of change of density with respect to time and space, the that should be varied, so we can say we are considering the flow is compressible, right? Mm. So the other part, we can say, uh, when the Mach number based on the fluid velocity is less than zero point 0.3. So the incompressible flow machines are those machines which handle either the liquids or gas at a low Mach number, right? And thus any hydro turbo machines, it is pump and hydraulic turbines as well as the commercial blower and fans are part of this incompressible flow turbo machines, right? So as I told you, this is depends on the density of air or density of water, or we can say density of fluid, right? So we cannot neglect the density change effect, right? And as that happens at a high Mach number, so we can say the flow is of compressible flow type, right? And this includes the high speed, high pressure ratio, high pressure compressors, high pressure steam or gas turbines, right? So based on the type of the flow and based on the direction of the flow, we have discussed here. The next part is the axial flow machine. So in axial flow machine, the irrespective of the fluid medium and the type of the flows, the turbo machines are classified as we know that the axial, radial, mixed flow, that is depending on the flow part, right? And we will also through each of these one after another, right? So what do you mean by the axial? What do you mean by the radial and mix? So we will start with the first the axial flow machines, and here the fluid flow parallel to the axis inside the rotating blade passages. So please note that the the flow is coming with the flow is coming in x directions only, right? So we are considering this is known as the axial flow. When the flow is coming with the x direction and goes to the y direction, so radially both flows are mixed, x directions as well as the y direction. So we can see this is known as the mixed flow, right? And mixed flow is also a very important role in turbo machinery part. The next part, that there are different types of compressors. So as we discussed here, the positive displacement machine, the axial flow compressor, centrifugal flow compressor, as well as the in turbo machinery part, the turbine part is also there. So So the intact, compression, combustion, exhaust. So these four words are very familiar in turbomachinery field. So the positive displacement machine that operate by the trapping of gas and forcing it into the smaller value. So the two main basic designs of the positive displacement machine, and that is known as the rotary type and reciprocating type. The another part that is known as the centrifugal compressor, and in centrifugal compressor that operate by the accelerating the gas, that converting the energy to the pressure, right? So the main basic to design for the centrifugal compressor, the first one is the centrifugal, the another one is the axial. So in turbomachinery, the thermodynamic is a very important part. HS diagram, the H is a entropy enthalpy diagram, HS, the TH diagram, the velocity triangle, compressors part as well as the turbine part, and the very useful equation that converted to blade from the airfoil, right? So quickly we'll go with the thermodynamic first law and second law. So we know that we will start with the first law of the thermodynamics, right? So the first law of the thermodynamic is essential the conversions of energy. And when we talk about the first law, so we talk about the interaction of heat and work, right? And heat and work, the changes in different form of energy. Energy is very important. Energy is very important word in in thermodynamics. So let us say we have a system and some heat is added to the system and some work is done by the system. So the first law tells that there is a property called energy of the system which will change as a result of interaction of heat and work with the system, and we get the first law of thermodynamics. In second law of thermodynamics is a very fundamental law because it gives an additional qualification on the energy transfer. So while the first law talks about the conservation of energy, and second law will add a restriction. So first law does not tell you whether 100% of the work that can be converted into the heat on vice versa, right? So the second law puts a restriction on the direction of the flow of heat and work. So for example, we know from our common experience that water flow falls from higher level to lower level spontaneously, right? And heat flows from higher temperature to lower temperature. That's naturally. Okay. So the first law does not really say that such a process is not possible, right? And the second law brings in the directional aspect. So you can actually take water from the ground floor to a multi-storied buildings, top of the multi-storied buildings by using a pump. Okay, so that means you have to put in an external agency to supply the work. So this concept, the directional constraints are added by the second law. And the second law also gives rise to a property called entropy. And it is defined that we know that the ds is equal to delta q reversible, right? So we are talking about the reversible process by T. Okay. So the total energy is transfer. Okay, so first law and the second law is very important in turbomachinery field, as we discussed here. And look at this, here we have a image of the engine. The inlet part is there. So actually what happened when we mount stator and rotor blade inside the casing, inside the solid casing, right? So here we can clearly see the stator vane is fixed and rotor is continuously moving. So what is the working of stator and rotor in axial flow compressor, right? If we are talking about the one blade of stator and one blade of rotor, so we can say this is known as the first stage. Okay. If we are talking about the second stage, so The second stage has a two blade of rotor and two blade of stator. Okay, so here the pressure and velocity variation inside the rotor and stator. So the main working principle of rotor, as I told you, to adds the salt to flow, right? To add the kinetic energy to flow with half rho v square. Okay, we have to increase is the total energy that carried in flow by increasing the angular momentum. So due to this reason that we can see here the working principle of rotor and stator, the velocity part in rotor case is increases. Look at this here, the velocity properties using the rotor blade that we can rise. And what actually in pressure rise? Look at the, if we are talking about the rotor blade, the pressure is increases. Okay, but what is the main working principle of stator? The main working principle of stator is to remove the swirl from the flow, right? And this is not a moving blade. That we know that. So due to this reason, we cannot add any net energy to the flow, right? So the converts the kinetic energy associated with swirl to internal energy by raising static pressure flow. Okay, so using the rotor and stator with number of stages, we can rise the pressure, we can increase and decreases the property of velocity, right? So this is the three-dimensional image, and look at this. This is a uh, center line. This is the center line, and this is the diagram of the arrangement of rotor blade and stator blade. Okay. The most important thing is loss to convert the energy. So the total energy that is transferred, right? So the transferred from the impeller, that is the rotating blades, to the flow, right? So only a part of it, maybe a major part of it, but only a part of it, it gives to the transferred to the fluid in an useful fashion, right? And there is an energy rise across the turbo machines. Okay, so where the loss accounts for the remaining portion. So in case of turbine, the total energy available with the fluid. So we cannot extract the energy that goes into the blade. So in the form of torque, the power produced is only a fractions. So maybe a large fractions like 80%, 90%, or 100%. So there is a component called loss, right? So engineer working in turbo machines company. So what you would like to do is try to minimize the loss, right? Uh, Suppose we will not minimize the loss practically, so we can reduce the efficiency, right? So we have to reduce the loss and rise or increases the efficiency. Okay, so in the difference between the useful specific energy, that content of the flow between the two ends of the machine, that is defined as the specific work, and this specific work done between the inlet and outlet of the machine, right? So the specific work converted into the energy per unit mass. So there are a different type of loss in turbo machines, like internal loss as well as the external loss. So internal loss and external loss, the different type of loss, and we come across and how to account for it, and finally how these lead to efficiency. Okay, so we can say that there are two different type of loss, as I told you, the internal loss, or the losses taking place in the flow part, and external loss, or we can say the losses taking place outside the flow part. So the first will quickly the classification of internal loss, the losses taking place in the flow path, the hydraulic, the leakage, the disc friction loss, and the return flow loss. And for the external losses that taking place outside the flow path, that due to the friction in the bearing sealing, the fluid friction at the shaft and couplings, etc. Right? and the power consumed by the auxiliary equipments, so like oil pump, the speed regulators, which are driven by the shaft of the pump. Okay, so due to time constraint, I will not talking about the much details about the losses. So this words is very important in turbo machinery, and always we have to minimize the losses. So the next part, the design process. How can we design the turbo machinery part? Uh, how can we follow all the processes, right? So this is also very important case in turbo machinery. So in design, the first of all we have to define the problem, right? So here we are talking about the turbo machinery. So there are lots of rotating element inside the engines, right? So starting with the axial fan. So axial fan has a huge diameter, and it has a very high number of blades. Then after the air is sucked from the atmosphere, some process is going on, and using the axial flow compressor, using the number of stages, we can we can rise the pressure, we can minimize the velocity, and there are different types of axial flow compressor stages: the low pressure compressor, high pressure compressor, and then after the combustion part is there, right? So ignition process happen inside the combustions. Then after the turbine part is there. So using this component, we can minimize the temperature. Then after flow goes exhausted is in nozzle part, right? So whatever we will discuss here, or we discussed in the turbo machinery part, or suppose we have to design the compressor. So first we have to establish the problem, right? So do the background research, right? So literature survey, very important. Okay, so the specific requirements, so we must go to the specific requirements. Then brainstorming is very important. We have to evaluate, we have to choose the solutions, right? So based on the result, based on the data, based on the design changes, based on the prototype, we have to test it again, and we have to improve our design. We have to develop, and we have to develop the we have to develop, and we have to prototype solutions, right? So we have to uh, follow all the processes. Then after we will get the result, right? So we have to follow the design process. There are different types of softwares available for the design engineering. So using this software, using this technique, using this programming language, we can we can develop the test record, we can develop the machines, right? So the software for the design engineers, like programming language. So there are different types of programming language, like MATLAB, the Scilab, Python, C, C++. The CAD software is there, that like the AutoCAD, Creo, SolidWorks, the CATIA, Solid Edge, right? So there are different types of meshing software is also available, like the NC Mesh, MeshGen, iSAM, the TurboGrid, Gambit, Pointwise, Grid Flow, the post processing and the solver. Using the post processing and solver, we can get the result, right? So these all are the softwares for the design engineering. Okay. So the knowledge of the coding tools, knowledge of the gate tools, knowledge of the meshing tool, and the analysis part, as well as the post processing portion, is a very important case. So we must to know all about, right? So the word computational fluid dynamics, where we can use the computational fluid dynamics, why the CFD, what is the procedures, right? So computational fluid dynamics, why the CFD? The theory, the Albert Einstein said that the theory is something nobody believes. The expect except the person who made it, right? An experiment is something everybody believe except the person who made it. Okay, so the introduction part of the computational fluid dynamics. Computational fluid dynamic is the analysis of system that involving the fluid flow, heat transfer, and associated phenomena such as the chemical reaction by means of the computer-based simulations. So, a tool for solving the partial differential equation or the three fundamentals equation, like we know that the conservation of mass, conservation of energy, and conservation of momentum equations. And this computational fluid dynamics has on advantages as well as the disadvantages. So there are different types of method like experimental method, the analytical method, and as I told you, the numerical or we can say computational fluid dynamics. Right. So we will not much go into the details in the computational fluid dynamics. So directly I am jumping to the CFD processes. So pre-processing, post-processing, and solving. So these three are very important. Suppose we have to solve the problem like a flow over a blade, right? So in pre-processing, first we have to generate the airfoil using the x and y coordinates, right? The x and y coordinates both are simply available in the airfoil tool in Google, right? And that directly import it, that create the mesh over there, create the mesh, generate the domain, then after apply all the boundary conditions. So this is the part of the pre-processing, right? Then after the solving, we have to solve the equations. We have to solve the equations by applying the boundary conditions. So we have a laptop or we have a desktop with a high RAM, so we can easily solve this problem by applying the boundary conditions. So we got some colorful images, right? But is it really true or not? Is it really appropriate or not? That so we will very much confused. How can we say that this result is right or wrong? So this is very important, right? This is very important in computational fluid dynamics. So in turbomachinery part, suppose we will discuss about some of my students. They did the project about the flow over the blade, right? Flow over a axial fan. So with number of blades they have created, and after that applying all the physics, and they got this type of results, right? So here there are different types of colors available. So we will discuss about it. Also, the velocity streamline, we can also identify the how much pressure generated over the how much pressure is formed over the suction side as well as the pressure side, right? So this is the three-dimensional analysis, right? So this is the inlet part, this is the outlet part, this is the upper wall, this is the lower wall, right? The periodic boundary condition is very important in computational fluid dynamics for the turbomachinery part, right? The periodic boundary conditions. What do you mean by the periodic boundary conditions? Suppose in axial flow fan, I have a total 10 number of blades, right? So I'll take it only the one number of blades with accurate dimensions of the control volume, right? Then after I'll applying the meshing part. I'm applying the boundary conditions and to get the solutions. The major part is missing, and that this is known as the Navier-Stokes equations. As I told you earlier, the conservation of mass, conservation of energy, and conservation of momentum. So the momentum equations, the Navier-Stokes equation is very important. Uh, inside, actually, what happened inside the screen, right? So as an engineer, we must to know. As an engineer, we must to know using all the languages we can find it out. Okay, and here, as I told you, the colorful images says that the flow is coming from the inlet part and goes to the outlet part. But inside the inlet and outlet, the model is mounted, and here the model is played. Okay, So we have to observe how much pressure form over the plate as well as the below the plate. Okay, so using this technique we can easily know that. And here this is indicating, the red color is indicating the maximum value of velocity or pressure. The dark blue color, that is indicate the minimum value of velocity or the pressure. Okay, so here I have one small video about the velocity particle track animation. So look at this. If we are tracking the particle of air, look at this. Okay, once again I'll play. Okay, so this particle of air has on translational, rotational, and vibrational of the motion, right? So what happened here? The particle is coming from the inlet part. Due to the boundary condition, this particle of air that travel over the blade, but due to the shape of the body as well as the boundary conditions, at this point, if you observe that at this point has a maximum velocity. This is the velocity streamline, right? So it has a maximum velocity, and look at this. At the lower part of the backside of the blade, it has a low velocity compared to this point, right? So this particle of air that travel from here to here, we can say leading edge to trailing edge, right? Then after exit from the system. Okay, fine. So as I told you, the pressure contour on the blade, right? So the pressure contour on the blade. So pressure contour on the blade, look at this. The pressure contour at the suction side as well as the upper part as well as the lower part. Okay, so this is indicating the upper part of the plate, and this is indicating the lower part of the plate, right? So the at the first slide we discuss about the lift force, right? What do you mean by the lift? We have to improve the lift, we have to minimize the drag, right? So we have to apply all these fundamentals here, so that using the physics, as I told you, the flow simply passes over the flat plate. Sorry, flow passes over the blade, the pressure contour on the upper part. So this upper part and the lower part, that significant with different values. So we can say that at the suction side as well as the pressure side, the lower part of the blade has a maximum value compared to upper part. So this image is proof that. The another group, they arranging the stator and the rotor blade with number of stages. And we increase or if we increase or reduce the distance between two stator blade as well as the rotor blade, so what happened, right? What happened in between the two blades, right? So they increase and reduces the distance between two blades. Okay, and they found that if we increases or reduces the distance between the two blades of the rotor, so the velocity form with maximum value. Then at the trailing edge, after the trailing edge, look at this. Look at this. The when the number of blades, when the number of rotor blades, this is the first stage, second stage, third stage, fourth stage, five stage, six, seven, eight. They did with 10 stage. Okay. So if we observe the first stage, fifth stage and tenth stage of the blade, So we observe that the turbulence form in the first stage. Now look at this. The turbulence is generated near the trailing edge, and at the fifth number of blade, the turbulence is not generated near the trailing edge. Turbulence form, right? But after covering some distance, okay, and got the maximum value of velocity. And look at this. At the end of 9 or 10 stage, the due to the very high velocity, due to the very high value of velocity, and we know that the working principle of axial flow compressor, right? So turbulence is formed at this part, right? So with this statement, this is the pressure side. This is the pressure control. So, as I told you, the computational fluid dynamics is a powerful tool to solving the complex flow in engineering system. And however, extreme care should be taken while generating the geometry and grids, using the flow models, boundary conditions. Some apply the material properties, convergence criteria, proof of grid independent test, right? So, as an engineer, we must to apply some apply the physics over there, and we will get the accurate answer, right? Unless the proper inputs are given and solution is checked, the solution we get may not be correct and clear, right? So this computational fluid dynamics is a very powerful and very complex software, and we must to identify how can we improve the result, right? So using this technique we can improve the result, we can improve the efficiency in turbomachinery field, right? So I hope you enjoy the tour of the not a colorful diagram, but we can see computational fluid dynamics. All right. So thank you very much, and I would like to request all the participants wear your mask properly. So this image is directly taken from the NC's website. They did the analysis. If we are not put the properly mask, so what happened, the droplets can enter it, and this is the comparison between the loosely fitted as well as the properly fitted mask. So the loosely fitted mask, the droplets can easily enter, and the proper fitted mask, look at this, the analysis did with the other particle of air that cannot enter, right? So I request to all of you, wear a mask, stay safe and stay healthy. So thank you very much.
Okay, sir, we have one question. What are the flow models, sir?
Yes, very good questions. Flow models, we can say about in the computational fluid dynamics, there are different types of turbulence model is there, right? So RSM, K epsilon, K omega, the DNS, LES. So there are different types of Reynolds. There are different types of Reynolds turbulence model is there, right? So in turbomachinery field, many of the researcher conclude that the K epsilon is a very appropriate model for the case of suppose we are doing the analysis of the cooling blade technique, right? Cooling blade technique in turbine part, right? So the K epsilon is a very good model, as well as in axial flow compressor is also the for the case of fan For the case of compressor, for the case of turbine, the K epsilon is very nice, very accurate model in CFD field. And for the case of combustion, right? So here the chemical reaction is going on, right? In combustion, the air and the fuel both are mixing together, right? So the DNS and LES is a very important model for the case of combustion.
So one student again, that same student asked, what is K epsilon? I mean, he is first year student. That's why.
Fine, fine.
So he's
The
asked, what is K epsilon
K
model?
epsilon, yeah. Uh, the computational fluid dynamics, as I told you, there are a different types of models, right? So the K is a kinetic, E is a epsilon, right? If we talk with the full name of the model, kinetic epsilon model, right? So there are different types of equations in K epsilon. There are different types of equations in kinetic K omega, right? So this is the one model. So there are using the equations, they made some codings, and using this technique we will solve the iterations, right? So using this technique we can say that whenever the day is going on, the all the researchers are doing the research in the field, and they conclude that this model is very appropriate for the case of turbomachinery, or in mechanical any part, right?
Okay, sir. One more question. How we can apply Newton second and Navier-Stokes equation over the model, flow model?
Yes, yes. Navier-Stokes equation. Navier-Stokes equation. The I think we must to know the meaning of conservation of energy, conservation of mass, right? If we don't know the meaning of conservation of energy and conservation of mass equations, so we cannot understood the momentum equations. Momentum is nothing but this is the mass into velocity, right? So we know the equation of the d rho by dt. So first we identify the which type of flow we can solve. The flow is compressible, or the flow is incompressible. So based on the flow we can solve the equations, right? So the diffusion, the source term is there, the diffusivity is there, right? So the general transport equation, or we can say scalar equations, right? So this is known as the Navier-Stokes equations.
Okay, sir, there is a question. Like student has asked, what is difference between axial pump and centrifugal pump? Uh, like axial flow, in which order we are taking axial pump? Hello.
Hello, can you hear me? Please
Yes,
repeat the question. Please repeat the question.
sir, the question is, student has asked, what is difference criteria over the axial pump and centrifugal pump, and how we are applying axial flow over this engine, aircraft engine, turbojet engine.
uh, Axial pump and centrifugal pump. As we discussed earlier, the most common type of among the centrifugal pump is the radial flow pump, right? And the centrifugal pump uses the rotating impeller to create a vacuum in order to move the fluid, right? This is the meaning of centrifugal pump. And we know that the axial flow pumps that move fluid by drawing fluid into their axis, okay, and using the impeller to send the fluid out on the other side of the pump. So this is the major difference between the axial pump and the centrifugal pump.
Okay, thank you, sir. We are lack of time, and still some of question is more. So I would like to say, really, sir, very much thank you for we are sincerely thank you for giving students such as wonderful explanation and intro. You had given an introduction over the turbo machinery and CFD. That was very useful. And thank you for your generosity. You had accepted. I just said, and you had accepted for the webinar. That was very thoughtfulness, and I really appreciate. Sir, thank you so much, sir, for all the your time, and you had given your time over here. That is really appreciable. Thank you, sir. Thank you so much.
Yes, yes, yes. Thank you very much. Thank you very much, Nikita ma'am. And I hope you enjoyed my lecture, and it was a very fruitful from your side. So thank you very much.
Thank you, sir. Thanks a lot. And okay, sir.
Okay, bye bye. Have a nice day.
Bye bye, sir. Take care, sir. And stay safe over the corona.
Yes,
Okay.
yes, yes.
Okay, sir. Thank you,
Thank
sir.
you. Thank you.